All right, probably the most important thing I want us to learn about thermal energy is that it is energy. For historical reasons, thermal energy is often measured in calories or kilocalories. A calorie is defined as the amount of energy required to raise 1 gram of water. Good gracious. There we go. 1 gram of water, 1 degree Celsius. So, 1 calorie is defined as the amount of energy required to raise 1 gram of water, 1 degree Celsius. A kilocalorie is the amount of energy to raise 1 kilogram of water. That is about 1 liter of water, 1 degree Celsius. Okay, so, but the point is that what you're actually doing to water to raise its temperature is you're adding energy. And we're going to be measuring that energy in joules. You can certainly measure energy in calories, that's fine. And I imagine if you do a chemistry class, you will be measuring energy in calories. But like I said, in physics, we're going to measure energy in joules. And so the point is, when you're changing the temperature of an object, you are adding energy to that object. So thermal energy, when thermal energy moves across a boundary, it could be from one object to another object or from one side of the object to another side of the object. When thermal energy is moving, we call that heat. And heat is usually, the symbol we use for heat is Q, but it's really just thermal energy. It's how much thermal energy has been moved to cause something to happen. So the first thing we will learn is the amount of thermal energy it takes to change an object's temperature. So Q, the amount of energy that you have to move into an object to change its temperature is equal to the mass of the object times the specific heat of the object times the change in temperature that you want to have occur. So for water, this is 4,186.8 joules per kilogram degree Celsius. So if you want to raise a kilogram of water by 5 degrees Celsius, you need 5 times 4,186.8 joules. Okay, so that is an important formula for this section. But the important concept for this section, the idea of calorimetry, a calorimeter is basically a thermos. It's a device that's designed to not allow any heat to enter or leave the system. So if you have an isolated system where no heat can get in from outside and no heat can get out from inside, then that isolated system is going to have a total heat of 0. The heat is, the Q is going to be 0 for that system. Now, the only exception is if we have some sort of work happening inside the system, like friction. And friction usually does negative work. And so what happens is if friction does negative 50 joules of work, then that means the Q has to go up by 50 because what happens when you do work is you take kinetic energy and you convert it into thermal energy. And so we've gained thermal energy, and that shows up as Q. So this equation is the equation for an isolated system, a collection of objects where no heat is entering from the environment and no work is being done by the environment. And in that case, any conservative force happening inside the environment is not going to change the thermal energy. But any work done by friction or air resistance or other non-conservative forces can change the thermal energy. So for an isolated system, the work done by friction plus the change in thermal energy, Q, is equal to 0. All right, so 2 quick examples. If I stir a container of water, that's 0.5 kilograms of water, and I do 50 joules of work, how much will the temperature go up? So we're going to assume that the water is an isolated system. So that means that the work done plus the change in thermal energy, Q, is going to equal 0. When I do 50 joules of work, that's going to be negative 50 joules. And then the Q here is going to be the Q required to change the temperature, which is going to be MC delta T. Solving for delta T, I get 50 joules divided by the mass, 0.5 kilograms, and divided by C, the specific heat of water measured in joules per kilogram, 4,186.8. And that gives me the change in temperature. So 50 divided by 0.5 and also divided by 4186.8 gives me a change in temperature of 0.0239 degrees Celsius, which you might recognize as a very small change in temperature. And that sort of fits with our everyday experience. Stirring a glass of water doesn't noticeably increase its temperature, but in principle, we are adding energy to the system, and that energy has to go somewhere. And so it's going to go into changing the temperature of the water. All right, another quick example. If I have a 100-gram piece of copper at 80 degrees, and I place it into 200 grams of water at 20 degrees, what's the final equilibrium temperature? And the concept here is we're going to assume that this is occurring inside of a calorimeter, which is a bottle that's designed to make sure that no heat enters or leaves the system. So what that means is that any heat that leaves the copper has to go into the water. The total Q of the system is going to be equal to 0 because there's no work being done here by non-conservative forces. So that means that M of the copper times C of the copper times delta T of the copper has to equal M of the water times C of the water times delta T of the water. And actually, that's not the right way to write this, because what we should be saying is that the total Q is equal to 0. So the Q from the copper plus the Q from the water should equal 0. Okay, and the deal is, of course, this one is going to be negative because its temperature is going down, and this one's going to be positive because its temperature is going up. And when we add them together, we're going to get 0. All right, I need to look up the specific heat of copper because I don't know that, so I'm pulling up the textbook. Copper has a specific heat of 387 joules per kilogram degree Celsius, and of course water, the textbook here says 1,000 or 4,186, so I'll use that value. All right, so putting in my values, 0.1 kilograms times 387. Okay, I'm not going to put in my units, but units will cancel if we do it correctly. Times the change in temperature. Now, okay, the change in temperature of the copper is final minus initial. So it's going to be my final temperature minus 80 degrees Celsius. And since my final temperature is going to be less than 80 degrees, that should be a negative number, okay, plus the mass of my water, which is 0.2 kilograms, times the specific heat of water, and I'm going to use the value from the textbook, 4186, times the change in temperature. And the change in temperature of the water, again, T final minus T initial, so this should be T final minus 20 degrees Celsius equals 0. And since T final is going to be more than 20 degrees, that's going to be a positive number. And so now we've got an equation that we can solve for T final. All right. So let's see how we do this. 0.1 times 387. So this gives me 38.7 times T final minus 0.1 times 387 times 80 is 3096 plus 0.2 times 4186, 837.2 T final minus 0.2 times 4186 times 20 is 16,744 equals 0. Okay, so 837.2 plus 38.7 gives me 875.9. T final is equal to 16,744 plus 3096 is equal to 19,840. So T final is equal to this divided by that, 22.651 degrees Celsius, or let's see, how many significant digits here? It's kind of hard to tell from the problem. Let's just use 3 significant digits in our answer. 22.7 degrees Celsius is the final temperature. And you'll notice that that is a lot closer to the original temperature of the water than it is to the original temperature of the piece of copper. And there's 2 reasons for that. The first reason is that we had more water than we had copper. Okay, but that alone isn't enough. The real big reason is that the specific heat of copper is a relatively small number compared to the specific heat of water. It takes a lot of energy to raise the temperature of water. It only takes a little bit of energy to lower the temperature of copper. So the copper is going to lose its energy much, much quicker than the water. If we think of energy like a fluid, the copper is like a very skinny tank, and the water is like a really big tank. And the water starts out at 20 degrees, and the copper starts out at 80 degrees. And when we when we connect these tanks to each other, the water level of the copper goes down, the water level of this goes up, and we end up with a final equilibrium that's just a little bit over 20 degrees because it's very easy to lower the temperature of copper. It's very hard to raise the temperature of water. Okay, I will see you in the next video.